Hello, everyone. Before we get started this lecture, let's review the content in the last class. So in the last class, we started the exploratory data analysis, and first we saw two types of statistics. The first one is descriptive statistics. It is actually a summarization and graphical visualization. So in the descriptive statistics, the methods are summarizing the huge data into a graph or a few numbers such as mean, variance, or quartiles, and so on. And the other type of statistics is inferential statistics. Um, this is actually the statistics we learn in statistics course, the estimation and hypothesis testing. So we make hypotheses. Uh, for example, here null hypothesis and alternative hypothesis, and test them by some statistical tests, such as t-test, f-test, z-test, and so on. So the purpose of inferential statistics is estimating and testing the characteristics of population based on the samples. So the tests are applied to the samples. In precise, the test statistics are calculated by the samples. However, the tested hypotheses are about the population. So these are the conventional decision process in statistics. So we have population, and by sampling, we make sample, and the population is usually defined by some parameters. So we assume that the objects in population are generated by the some following some distribution, which is actually defined by some parameters. And the sample is namely sampled from the populations, and we usually calculate some statistics for these samples. And we can make some statistics from the sample, and these statistics usually summarize the characteristics of the samples. So from the sample, we can apply some descriptive statistics methods. And based on the results of this descriptive statistics method, we can make the inferential statistics method, which estimates the characteristics of population. In other words, by the inferential statistics, we can test the characteristics of the parameters which define the population. And exploratory data analysis, in short, EDA, is a method that discover the characteristics of data and structural relationship among them. So this exploratory data analysis is highly related to the descriptive statistics. The opposite word of this EDA is confirmatory data analysis. This confirmatory data analysis evaluates the reproducibility of models or effects. In other words, they test these model or this effect or these coefficients are statistically significant or not. So confirmatory data analysis focuses on the empirical test, on the collected information and evidences, which are usually derived from the sample. So this confirmatory data analysis is highly related to the inferential statistics. Okay. And for topics of EDA, resistance to damage to data and residual things and re-expression and graphical representation. So we saw the examples of these 4 topics of EDA in the last class. So we assume that the data is damaged so that the last sample 31 is changed to 310. Then the mean is changed from 15.8 to 41 to 41.2. However, the median is not changed. Median is to 15 is not changed. It remains as 15. So we can say that the median is more robust to damage to data than the mean. In other words, the resistance of median is better than that of mean. So in the viewpoint of resistance, median is preferred to mean. And the next one is the residual. So residual is one of the important concepts in the statistics, which usually defines the deviations or errors. Okay, so remainders. So residual is defined as the observed sample minus the main trend, and this many things can be this main trend. For example, for this example, the median or mean can be main trend or the regressed line. If we use the regression analysis, the regression line can be a main trend and some other things. For example, if we assume some model, then that model can be a main trend, and the error between the observed sample value and the predicted value by the model can be also treated as residuals. So observing these residuals help us to understand the characteristics of the data so that we can find the other patterns that we couldn't see before. And the expression of data means that to transform the original variables to the other variables, for example, taking log or taking inverse, taking square root, anything, so that we can easily find the patterns more. For example, the linearity or symmetricity. If you see the example in the right side, we have 3 curved graphs. The first graph is y equals to ab to the x, and the second graph is y equals to ax to the b, and the third one is y is 1 over a plus bx. So the 3 if we do not have the equations here, it's somewhat difficult to match its equation to each graph, the corresponding graph. However, if we take some log or inverse transformation to the variables, for example, we can infer the form of the equation easily. For example, the first graph, if we take the log to the y variable, then we can make the linear relationship between the log y and x. However, in the second graph, we can find the linear graph between the log x and log y, not the original x. And the third one, if we take the inverse to the y, then we have the linear relationship between the 1 over y and x. Okay, so that we can easily distinguish the form of the graph or form of the equation for each graph. And the graphical representation, you can easily find the graphical representation can help us to understand the structure of data by the histograms or scatter plot. And we saw the data types called quantitative data and qualitative data. We have the nominal and ordinal variables for the qualitative data, and we have discrete and continuous data types for the quantitative data. And we saw the cross-sectional, longitudinal, panel data. Cross-sectional data is the data collected at a specific time, and longitudinal data is the data observed following the time. However, the cross-sectional data usually handles several variables simultaneously. However, longitudinal data are more focused on small number of variables, 1 or 2, so it is much focused on the time series analysis. And the combination of these two are for panel data. So the panel data has several variables observed following the time. So if we have panel data and if we only use data at certain time, then it can be considered as cross-sectional data. And among the panel data, if we use certain variables, a small number of variables observed following time, then it can be considered as longitudinal data. And we have the nominal scales and ordinal scales, interval scale, and ratio scale, 4 scales of data. So nominal scales are the distinctness. For example, if two variables are the same or not, the ordinal variables are the orders of the feature values. And interval scales define the difference between two feature values or attribute values. However, it does not use the absolute zero concept. So zero does not mean nothing here. Zero is just zero. Zero is just one less than one, or one more than minus one. Zero does not have any special meaning. However, in the ratio scale, zero means zero. In other words, zero means nothing. So in the ratio scale, the ratio between two feature values are defined. Okay, this was the review in the last class. And say we will start from this page. So we will see several um, representative values of the data distribution or sample. So the first part is about the representative values of the location information. The location information means where the data distribution locates. So here, or here, or here. Okay. So the first representative value of this location information is, of course, the mean. However, we will here use the specific term of the mean, which is arithmetic means. So I think you guys all know that there are three types of mean. First one is the arithmetic mean, and the second one is geometric mean, and the last one is harmonic. Harmonic. Harmonic mean. Okay. So if there are two values A and B, the arithmetic mean of A and B is defined as A plus B over 2, and geometric mean is defined as square root of AB, and the harmonic mean is defined as AB over A plus B, which is right. Yeah, I think it's right. So here these are the definitions of three means, and here we first see the arithmetic mean as the location information because it is defined as sum of all the observations divided by the number of observations. So this is the very conventional concept of average and very easy to understand. So the population mean is usually denoted as the mu, Greek letter mu, and the sample mean is denoted as x bar. So as mentioned, it is the sum of the all observations divided by the number of observations. So there are many characteristics of arithmetic mean. For example, the arithmetic mean uses all observation. It does not omit any observation. It uses all observations. So in other words, it is affected by all observations. If one observation is changed, then this arithmetic mean is also changed. And the arithmetic mean is unique for given data. So if data are given, then there are only one arithmetic mean value, not 2 or 3 or more. And sum of the observations minus the arithmetic mean equals to 0. We can prove it. X bar equals the 1 over n summation j equals to the n xj, and then summation I equals to 1 to the n xi minus x bar equals to I equals n 1 to the n xi minus over n summation j equals to n to the xj. So if we take 1 over n to the outside, then summation I equals to 1 to the n xi minus summation j equals to 1 to the n to the xj. So it is 1 over n to the summation I equals to the I equals 1 to the n. N minus 1 xi, not here, okay. So let's expand this summation, okay. Then 1 over n over here. The first term in the summation becomes n x1 plus n x2 plus n xn, and the next term is minus n multiplied by x1 plus xn, okay? So all terms are already cancelled, so it will be 0. So this one will be 0. So as I mentioned, the arithmetic mean is all observation, so it is affected a lot from the extreme values. And we can also use the weighted mean. In the weighted mean, each observation has different weight. Usually we denote this weight as Wi. And sometimes, or usually, we have some condition that sum of Wi equals to 1. Sometimes we do not have this condition, but we usually have this condition. So the weighted mean xw bar is defined as sum of Wi multiplied by xi over sum of Wi. If it is 1, then it can be just written as Wixi. So by changing this weight, we can modify the importance of each observation. In other words, the degree of effect of each observation on the weighted mean or the mean, the representative value. There are some other representative values for the location information, which are called the median and mode. The median is the value located in the center when the entire data are sorted in order of size. So we order all the data from the minimum values to the maximum values. Then the values in the center is the median. So if the number of observations are odd number of observation is odd number, then the median is defined as x n plus 1 over 2. So if we have 5 observations, in other words, n equals to 5, then x 5 plus 1 over 2, x3 is defined as the median, as the centered value. However, if n is even, have 6 observations, we do not have centered value. So in this case, we take the average of these two values. So x3 plus x4 over 2. And the mode is defined as the most frequent value among the given observations. So it is very popularly used to find the representative value for nominal scales because nominal scales attribute values does not have any orders or scales or amounts, so we cannot find any mean or median for the nominal scale values. So in this case, we use the mode. In other words, the most frequent attribute values. Here are nominal, for example, here are nominal attributes, for example, color. So we have red, red, green, green, red, blue, blue. Then the number of reds is 3, and number of greens and blue are 2. So the mode of this color attribute is red. So these are the comparison of error-set mean and median and mode. If we see the graph at the center, which is the perfectly symmetric and barrel-shaped graph, then mean and median and mode are the same. For example, it's just normal distribution. However, the graphs are skewed. For example, the graph on the top, which is the right, skewed graph. And the second one is the left skewed graph. The skewness, okay, we will say about the skewness a little bit later. However, the right skewed data. The mean is here and median is here and mode is here. And however, the left skewed graph, the mean is the most left side and median locates here and mode locates here. So mode can be defined if we have this continuous distribution, the mode can be found the top of this density graph, okay, which is the most frequent value. And the next is the next part is about scale information. Scale information is how the data points or distributions are distributed. For example, distribution is this shape or this shape. How it is deviated or distributed, or how large its variation. So the first one is the range. Range is can be calculated very simply. It is just the difference between the maximum value and minimum value. So if the range becomes larger, then the variation of data becomes larger. So we have two graphs, this one and this one, and the second one, okay, let's say A and B, E has larger range, of course, than A. And the advantage of this range is very simple. However, this range is very sensitive to the extreme values, and sometimes it cannot be easily calculated. For example, if we have a normal distribution, range is actually infinite because minimum value and maximum value of the normal distribution cannot be found. However, if we use the samples, not the distribution, then we can find the range. And then the next one is mean absolute deviation. So this is the average distance from the arithmetic mean. So we have the absolute difference, the sum of the absolute difference from the mean over n. So we know that not the absolute value, this one is 0, we know. And however, we take the absolute value here. So this value is not 0 and always greater than or equal to 0. So the A and B again, this example. Of course, okay, let's make another example here. We have two sets A, three data points, -1, 0, 1, and B, -2, 0, 2. We know that the arithmetic mean of the set A and B are all 0. However, the mean absolute deviation, this one is over 3, and this one is over 3. Okay, it's twice, as twice as this one. The range of A 2, 1 minus minus 1, and range of B is 4. Another scale, the representative value of the scale information is variance and standard deviation. Very famous, and I think all of you guys already know the variance and standard deviation. The variance is the also measure for the variation of data is average squared, square distance from the mean. So population variance can be average square distance from mean, and sample variance is the also average square distance from the mean. However, here is n minus 1 rather than n. This change is called Bessel's correction. And this Bessel's correction is many the statistics textbook explains this one as with the degree of freedom. For example, this x bar uses the all the x's, so the degree of freedom becomes n minus 1 rather than 1. That is also correct. However, this Bessel's correction is can be proved by the proved rigorously by to assume that is the expectation value of the S square becomes sigma square, or in other words, S square is an unbiased estimator of here. To satisfy this condition, if we expand all the mathematical things we can prove, here should be n minus 1 rather than 1. We will not cover this Bessel's correction precisely. Maybe you guys can find the proof of this Bessel's correction in many ways. Just find it from YouTube or ask your statistics professor or anyway. And the standard deviation is just square root of variance. So why we take square root of variance to make standard deviation? Because then the standard deviation, unit of standard deviation, becomes the same with the observation. Actually, the unit of the variance is squared because we use the squared distance. So it is the unit of variance is the square of the unit of observation. However, the standard deviation uses the same unit with the observation. So here are comparison of variance and standard deviation. They are both measures for the variation of data. The smaller variance and standard deviation, the closer data instances locate to the mean. So variance and standard deviations are always greater than or equal to 0. If they are 0, it means that all the instances have all the same values. Okay, this one is important. Okay. And as I mentioned, the unit of observation and standard deviations are the same, but the unit of variance is a square of it. And they are also affected by the extreme values because they also uses all the observations. So here are example of the variance and standard deviation. The dataset 1 and 2 has the same mean, x bar equals to 50. However, the standard deviation of the second dataset is twice as the first one. So we can easily see the first one is distributed in smaller area than the second one. Okay. And the other representative value for the scale information is coefficient of variation. So coefficient of variation is defined as S over X bar multiplied by 100. So it uses the percentage value. So it is actually the ratio between the standard deviation and mean. So the one good thing for this coefficient of variation is that because the standard deviation and mean has the same unit, so it does not have any unit here. So if we have different data sets with different units, then we can easily compare them with the coefficient of variation. It is just ratio of standard deviation to its mean. If we multiply it by 100, then it will different value. So how much percent of the standard deviation compared to the mean? And the remaining property of the dataset are skewness and kurtosis. So first we saw the location information, and second we saw the scale information. So the location information covers where the distribution locates, and the scale information covers how it is distributed or its variation. Then the skewness is the measure of asymmetry. How it is symmetric or asymmetric. Okay, so it is calculated like this, and if the skewness is 0, then it means it is symmetrically distributed. So its left side and right side are the same. However, if the skewness is positive, it means that we usually call it right side skewed or right skewed or positively skewed. It means that it has long tails in the right side. For example, like this. For this one is the right skewed. And the negative skewness means the opposite, of course, the left skewed, left tails in the distribution. So, and if the magnitude of this skewness is large, then it is more asymmetric. Like this, like this. So this is the positively skewed graph, and this is the negatively skewed graph, and this is the not skewed or symmetric graph. And kurtosis is measured for the peakiness of the data distribution, how it is peaky. For example, like this or this. Okay, this is the more has large kurtosis. However, it is important, really important. Kurtosis. Many textbooks explains this kurtosis is a measure for the peakiness. However, it actually kurtosis measures detailedness, not depictedness. What it means is that kurtosis is actually tail is fat or thin compared to the normal distribution. So it is usually calculated like this. Sometimes here's -3 is not here. So if you do not want to -3 here, then just put 3 here. So the standard value becomes 3 rather than 0. However, if we see -3 here, then the referential value becomes the residual. So in this textbook, we use this value, which contains the -3 in this kurtosis. So kurtosis 0 means that it has the same tail with the normal distribution. And we kind this distribution as mesokurtic. However, if kurtosis means positive, kurtosis is positive, then the distribution has better tail distribution than the normal distribution. So this is normal distribution, then it has better tail. Better tail means thick tail, and it is usually more peaked like this. So it's lack of shoulder. It does not have shoulder, and we call this kind of distributions as leptokurtic distributions. The negative kurtosis means the thinner tail distribution than normal distribution, and it's less peaked, however more shoulders like this. This is the platykurtic distributions. And the magnitude of these kurtosis values means the degree of difference from the normal distribution, like that in the skewness. So if we here, the orange line is the normal distribution, then the leptokurtic distribution comes like this blue line, and platykurtic distribution becomes this green line. And here we cannot see the tails in detail. However, if we go more, this leptokurtic distribution is the diminishing rate of this leptokurtic distribution is the least, and the platykurtic distribution is the most. And the next part of the chapter 2 is the examples of the EDA, relative frequency distributions, and histograms, and stem-and-rib diagram, box plots. And we will see the details of these methods during the several chapters. So let's finish chapter 2 here, and let's start chapter 3 from the next class. Thank you for listening.